Welcome back to elementary statistics. In this video, I want to introduce you to the central limit theorem. The central limit theorem is easily the most important idea in statistics. No, I did not say the most important idea in this course or the most important idea we're going to talk about this semester. The central limit theorem is the single most important thing in all of statistics. The central limit theorem allows statistics to work. We are going to, after this lesson, spend the rest of the course using the central limit theorem in order to build tests and talk about things called statistical significance. That's for the future. For this video, I just want to explain to you what the central limit theorem is, what it does, and how we work with it, and how we discuss everything that we're going to be building on for the rest of the course. Let me get my head out of the way. And first thing I want to do is the central limit theorem, or the discussion around the central limit theorem, will finally address the question, why do we use a different variable for the mean and standard deviation of a sample compared to the mean and the standard deviation of a population? And the answer to that question is that in this lesson and for the rest of the course, we are going to be studying what are called sampling distributions. Specifically, sampling distributions of sample means, but sampling distributions will sort of do the job for now. Right? You can sample other statistics. You can do a sampling distribution of standard deviations. You can do a sampling distribution of proportions or any other thing, but means are the ones we have studied the most, so that's what we'll look at here. The idea of sampling in and of itself is something we've already worked with. If you have a population that you want to study, you go out and you collect a couple of members of that population that you believe are going to serve as a representative sample, and you do a statistical analysis on the distribution formed by that collection of members of the population. Now, you can do a sample on a population. I can look at a different sample on the same population, and the values we are going to get will be slightly different. What we want to look at here is how different are those values going to be. And to do that, we form a sampling distribution. The members of the sampling distribution are the means of the samples. So you take a sample, it has a mean x bar 1. I take a sample, it has a mean x bar 2. Joe takes a sample, x bar 3. Megan takes a sample, x bar 4. And so on and so on. These samples themselves form a distribution. So the sampling distribution of sample means is a distribution, and every member of the distribution, every element in that set, is the mean of a sample. And they are all samples of the same population. The first claim of the central limit theorem. This one, I think, makes the most sense of everything. The mean of the sampling distribution is the mean of the population. If you think about how sampling works, when you collect a sample, you are likely going to underrepresent low outliers, or you're going to underrepresent high outliers, because it's hard to pick outliers when you pick a sample. So you know that some samples are going to have a mean that is below the mean of the population. Some samples are going to have a mean that is above the mean of the population. On the balance, it should give you the mean of the population. If you take enough samples and the samples are big enough, you eventually sample the entire population and there you have it. Or maybe you sample the entire population 5 times over. But as you get more samples, as the samples get bigger, you should expect that the means of these samples are going to go closer and closer to the mean of the population. There's no surprise there. The most surprising result is the second one. The sampling distribution is normal. When you collect your mean of your population, it does not matter the shape of the population distribution. It does not matter the shape of the sample. You will always get the sampling distribution to have a normal distribution. Well, I guess always is a bit of a stretch. You need to have a big enough sample. The samples you collect need to be large enough compared to the population, and you need to collect enough samples to put into the sampling distribution. If you collect samples of 3 members each and you take 3 samples, who knows what that shape is going to be. But if you have samples that are large enough to be representative and you have enough samples, then they will be normally distributed. If you think about a skewed population, that doesn't look very skewed. Let's try that again. There's a very skewed population. You know that over here you have outliers, and you will probably collect 1 or 2 of those outliers, but you're not going to collect many. And so you're going to get a mean that comes here, or maybe there, or maybe there. Getting a mean that comes over here is going to be a little bit more challenging, but it could happen. But your means are going to become much closer together, because when you sample, you're not going to get this tail. The tail is going to be lost, and you'll get those parts in your sample, because chances are to make a representative sample that actually includes a member of those outliers, you have to have a very large sample. So there is some intuition as to why a sampling distribution always turns to be normal, no matter what the population distribution looks like. The standard deviation of the sampling distribution is sigma divided by the square root of n. Right? So sigma here makes sense. Sigma is the standard deviation of the population. N is not immediately obvious. First of all, what is it? N is the number of members of each sample in the sampling distribution. So each of these scores is the average, the mean of a sample. And each of those samples has n members in it. If there's some variation in that, it's not a big deal. It will wash out. But that's the basis we're assuming things on. Those three ideas give us the central limit theorem. Okay, so now we have the statement of the central limit theorem, or enough of the statement of the central limit theorem. Specifically, the central limit theorem goes into the idea of taking the limit as the number of samples in the sampling distribution increases, as the size of each sample increases, and having things approach these ideas. We're not worried about those kinds of details. We just want to know that this is something that we can work around for our purposes in this course. Okay, now that we have that, how do we use it? Well, we're never going to construct the sampling distribution, right? Collecting hundreds of samples and analyzing one distribution is an effort. Collecting many people's samples of the same distribution and analyzing them is not always possible. There are places where that's interesting. In political polling, there are a number of organizations that ask the same or very similar questions and try to get a representative sample of the population of people in the United States or wherever they happen to be centered for their polling. And so there's an interesting thing that can be done of analyzing the findings of all of these public opinion polls and trying to do analysis on that sampling distribution. We're not going to worry about that level of dedication. We're looking at, we collected one sample distribution, not one sampling distribution. Vocabulary and language is hard, and also talking is hard. All right, so we've collected our sample. We have done analysis on our sample. And we now have the question, how does our sample compare to the population? That's what the central limit theorem will allow us to answer. We have danced around this idea all semester. We want to be able to predict the sampling error, the difference between the sample statistic that we calculate and the population parameter that we are trying to measure, that we know must exist because no sample can ever be a perfect representation of the population. Sampling always loses information, and we want to know how bad is it. Now we have the tools that allow us to do that. We can talk about the mean and the standard deviation of the sampling distribution. We can look at where our sample fits on that mean and standard deviation to make predictions. To show you what I mean, I'm going to go back to IQ scores, which we've studied before. They have a mean of 100, a standard deviation of 16. Let's take a sample of 25 people at random. What does it mean to collect people at random? Again, I don't care. I don't want to address that question. We take a sample of 25 people at random, and we want to know the probability that the mean IQ, the average of the IQs of the 25 people in our group, is above 108. All right. So we are looking at X bar is 108. We are looking at N is 25. We have that mu is 100. We have sigma is 16. And, well, our z-score formula still works mostly the same. X minus mu over sigma. But for the sampling distribution, population mean is still the population mean. Instead of having an individual score, we have an average score. And our standard deviation, the standard deviation of the sampling distribution is sigma divided by n. So z is x bar minus mu divided by sigma over the square root of n. In this case, x bar is 108, mu is 100, sigma is 16, n is 25. And if I punch all of that into my calculator, I get 2.5. I don't think I need to keep going to the standard normal distribution table, but for z equals 2.50, it gives me that A is 0.9938. And remember, as we've talked about before, this table gives me the area over there. The probability that the group's IQ is below the number that I gave. I want above. So I need to take 1 minus 0.9938, which is 0.0062, or 0.62%. Right? So finding a group of 25 people, finding the average of their IQs, and finding that that average is bigger than 108 happens 0.62% of the time, a little bit more than 0.5% of the time. That's what the central limit theorem is all about. How can we use this? Well, one kind of obvious way of using this, I happen to have a group of people, and I have found the average IQ of the 25 people in the group that I have. And I was very surprised to learn that the average IQ of that group was 108. That seemed incredibly high to me. I did some analysis and I found out that yes, that is incredibly high. It is incredibly unlikely that a group at random has an IQ of 108. Not that a person at random has an IQ of 108. There's about a 25 or 30% chance of a person at random having an IQ of 108. But having that many of them is a lot more shocking. And so that might mean something. That might mean that the group that I'm looking at is not random in some way or another. I might later find out that the group that I've studied, that I selected at random, happen to also all have PhDs. Well, that's not representative of the population anymore, so my random sampling was not very random. Those are the kinds of questions that we're looking at. Those are the sorts of things we're trying to analyze using the central limit theorem. Right? I think that's a good place for us to stop on this video. As always, thank you for joining me. I'll see you next time.